So thank you very much for this nice introduction. It is a pleasure for me to be here. I can see several and many familiar faces. So thank you all for coming. So I'm very pleased that it is an honor for me to be given this opportunity to talk about my research on, let's say, the interface between synchrotron science and art. So this is what I'm going to talk about today. And the outline of my talk is going to be basically that one. I will go through a short kind of introduction, and then I will have a number of case studies. I don't know whether I'm going to have enough time to review them all, but I just want to give you a sort of a feel of the different types of topics we can look at using synchrotron radiation techniques. So interestingly, everything started here. Garman Harbottle, Barry Gordon, and Keith Jones back in 1986 produced that paper, and that was the very, very first paper which was talking about using synchrotron X-rays to look at ancient materials and artworks. So in that paper, they say a synchrotron X-ray producing device will present the research work in the field of archaeometry with a number of new possibilities. And what we mean by new possibilities, basically they derive from the fundamental characteristics of the X-ray beam. First of all, the extraordinary intensity. We can have a kind of a laser-like beam, very intense, much more intense than what we can have with an ordinary, conventional X-ray tube in a lab. So the first property is the intensity, high flux. The second property which we are using in this sort of studies is the energy tunability. So we have the capability to tune the energy, to optimize the energy, that is the color of the beam, and we can go from infrared through UV light down to X-ray beams. So we can change the color, and therefore we can go for soft energy beams to look at surfaces, or we can go for hard X-ray beams, for example, with a higher penetration power, and we can look at bulk materials. And we use also this energy tunability to do a lot of spectroscopy. So those two keywords, high intensity and energy tunability, that's the thing we are interested in. And what's happening is that in a number of studies on archaeological materials or artworks, we want to use those particular features. So in that same paper, they say, and our colleagues from BNL say, those techniques can be very sensitive. Because we have a very, very intense beam, we can look at very small samples, or we can look at very diluted samples. So we have a very high sensitivity. We can look at trace elements as well. And we can do that on bulk materials, such as ceramics or stones. But also we can adjust the beam size. We can go from a large beam down to a micrometer-sized beam. We use the beam as a sort of microprobe, and therefore we're able to look at very fine details, and we can obtain structural information on artifacts. Another property, another advantage of using synchrotron radiation beams, if we use such a point beam, kind of laser-like beam at a micrometer scale, we can go for, we can identify elements, and we can determine the elemental distributions inside the materials. So this, I'm going to show you a number of examples about this particular feature. And the last thing I would like to mention here is the ability to scan the beam across the sample, and therefore we have a lot of applications doing imaging, and this is really, over the past few years, I mean, that has been a very successful use of a synchrotron beam, doing imaging on a number of different materials. So Harbottle and his colleagues conclude saying there is every reason to believe that this instrument, synchrotron radiation facility, this instrument will quickly take a prominent place in archaeometric research. And it is interesting to realize that everything which is in that particular paper, the first paper, turned out to be very true. So this is here a graph which shows the publication rate. It goes up to 2006. After that, I mean, I stopped counting because you can see here we have a rapid, very steep increase of the publication rate. These are the papers reporting use of synchrotron radiation techniques applied to ancient materials and artifacts. So we are here in 1986, and you can see here it took a while before really the publication rate took off. So there were a couple of experiments in Japan and in France, but the other premiere was this particular paper here, and that was the first attempt to use synchrotron radiation to look at organic archaeological materials. And again, this particular experiment was done here at BNL. So that was that particular experiment was using this facility. This is the National Synchrotron Light Source, NSLS, which has been running on site here for about 25 years. So this is how a synchrotron radiation machine looks like. So that very first experiment by Keith Jones and collaborators on dental materials, that experiment was done in this particular place. So since that time, then, we had many more experiments. I started in the business back in 1997. So I think that was the first PhD work using synchrotron radiation techniques on archaeological materials. So I was supervising this work, and so this work was done at the ESRF, which is the European Synchrotron Radiation Facility in Grenoble. I mean, the place famous for its wine. So that was the beginning for me. I mean, this is how I started. I stepped in that particular business. It is interesting to see that about the same time, I mean, many more people got interested in that particular discipline, that particular topic. And this is here the first experiment, as far as I know, the first experiment done at Stanford. So this is an experiment done at the SSRL, which stands for the Stanford Synchrotron Radiation Laboratory in California. 1 or 2 years later, there is another paper, and this work was done at the APS, the Advanced Photon Source in Chicago, and so on and so forth. So these are really the, these are really the let's say the takeoff of activities using radiation, using synchrotron radiation on ancient materials. Right. So what do we want to do? I mean, the main motivations and objectives. First of all, we want to know how old the object is. What is the age of the object? We want to understand how the object was fabricated. So which ingredients, which recipes, what were the processes of fabrication of the objects? Where does the object come from? What is the market? What are the trade routes? And an important part is to check whether this material, this object, is a forgery or is a genuine work of art. Another important part of this work is to look at degradation processes. So conservation and restoration of works of art is an important part of this work, and using synchrotron radiation techniques help to elaborate strategies in order to preserve, conserve, or restore the works of art. So one thing which I should mention right now is that these are very difficult measurements. Basically, we want to use our techniques, but we want to use that on objects or on materials as is. So very often we have very valuable materials, in small quantities. We don't want to destroy those materials, of course. We don't want to destroy the objects. Very often we have a complex situation where we have several phases, a lot of minerals, a lot of organic materials, we have impurities, we have a lot of heterogeneities as well. The material or the object can be damage sensitive. We have to be careful about this. And we might need to look at a big object, a painting or a pottery, or we might want to look at very, very small, minute quantities of material. So this is very challenging, and as a result, it is interesting to see that when we try to do this sort of work, we also have to work on our own techniques. How are we going to adapt our techniques to this scope of work? So we need to push our techniques in order to have enough resolution, in order to be able to get quantitative information in such difficult situations. The keywords that I have here, I put here, this is interesting to note that people working in earth science or in environmental science, they have the same concerns. They have samples very heterogeneous, they have a lot of impurities, many phases, and basically we want to describe the object in a very accurate way. So let me give you a couple of examples of what I mean by complex materials or difficult materials. This is an exploratory work I did some years ago on varnishes of historical musical instruments. And so this is here a nice picture of those instruments coming from a collection, Cité de la Musique. This is the Museum of the Music in Paris. And if you take a small sample off the surface of those instruments, this is what you get. So this is a view here, a top view of the varnish. And if you make a cross-section in depth, then this is what you get. So this is a transverse cross-section. And you see you have a very complex situation, a lot of heterogeneities, and you have many, many different phases. You have a lot of minerals, and you also have a lot of organic materials. And basically the challenge here is we want to understand how those particular varnishes, how they were prepared, and what were the secrets of the master when he was preparing his varnish. So by characterizing the content of the varnish, we try to understand better the way those varnishes were prepared. So this is one example. The next example, this is something very common. This is just a sort of let's call it an archaeological nail buried in soil. So this is a rusted nail. So this is a typical example of very heterogeneous material. We have many phases, and we want to look at this object with a different length of scale. So this is the nail here. If we take a cross-section here, this is the image we get. So we see here the iron core, and which is surrounded by a number of layers. These are the corrosion layers. And then further out, you have the soil itself. So basically, we want to scan across this object, and we want to understand, starting from the pure component itself, the pure element, we want to understand the corrosion processes as we go from the core towards the surface. So we want to do that at different scales. This is what we get if we look at the same object at a smaller scale, and we can still go down. You see here we have a lot of precipitates, a lot of inclusions, a lot of defects, many layers. So those materials are in interaction between each other, and we want to understand, we want to look at those materials as is. And eventually, this is the work I was involved in. We want to look at the material at an atomic scale. So this is a work we did on a phase. We wanted to find out what was the phase, what was the structure of the phase. Interestingly, what happens here, if ever you remove the soil and the nail is back in air, some of those phases are very unstable. They decompose as soon as they are back in air. So we have to do this analysis kind of in vivo to make sure that we have all the phases without destroying the stratigraphy. We want to keep the layers intact, and we don't want to expose the phases, the ingredients or the materials. We don't want to expose those materials in air. We want to keep the object intact. So this sort of picture here is very typical. That's what we try to do in a number of cases at different scales. All right, so let me go through a number of examples. So this particular example here is a work done at the NSLS. So let me talk about the principle of the measurement here. This is what we call the X-ray fluorescence technique. So we use a beam here, so the material is exposed to the incident beam. So this is the excitation, and as a result of this excitation, we have a re-emission of X-rays. So those X-rays are re-emitted by the sample itself, and we have typical characteristic lines of emission. So we want to analyze this spectrum, and this spectrum is a kind of a signature or fingerprint of the elements which are present in the material. So once we understand those typical fluorescence spectra, we can do some imaging. So basically, we want to find out the distributions of the elements by step scanning the beam across the sample. So this is how the experimental setup looks like. This is a setup at X26, which is a beamline at the national synchrotron light source. We have the beam coming in here. This is a focusing optics system. The beam coming in here, the sample is there. We have here a video camera, and we have the detectors to collect the fluorescence emitted by the sample. And we want to analyze this particular emission. So this is the sort of special resolution we can achieve, a few microns, or we can even go below that, much below that in some cases. We want to look at trace elements. We want to do chemical speciation, so we want to look at the element distributions. And all those things here are indications of what the fabrication was, what is the provenance of the material, and what are the alteration products. So just to give you a sort of feel of the sort of beam or the sort of sensitivity we have, this is the size of the beam, a few micrometers size. And this is here a magnified picture of a hair. So this is about, let's say, 50 to 70, 80 micrometer across. So this is the diameter here, and this is how small the beam can be. And we can scan the beam across the hair here in order to get the elemental distribution across the hair itself. So we can have a very high sensitivity by doing this sort of experiment. And this particular technique was applied to that case here. This was done on a hair from this very famous character. This is Ferdinand II. He was king of Spain, and he was a very powerful man, and he was very well known because he's the person who supported the missions to the New World. So it turns out that this person died rapidly in 1516, and there was a question about why did he die? Did he get poisoned, or what is the story? So this is why this team, in collaboration with Lanzarote, who used to be a beamline scientist at the NSLS, this team looked at the elemental composition in the hair of this character. So these are the results here. This is here the typical fluorescence emissions spectrum. So we see here the signal coming from the zinc and the signal coming from mercury. And if we do that in what we call a tomographic mode, it's possible to find out what is the distribution of those particular elements throughout the object. So what you see here is the concentration of zinc across the hair. And here the concentration of mercury. You see here those hot spots here. These are high contents of mercury inside the hair. And this was done on a number of modern hairs as well as archaeological hairs. So there is evidence in that particular case that Ferdinand's hair contains a lot of mercury, huge quantities, and much above, way above what is permitted by the World Health Organization. So the current thinking is that apparently, Ferdinand was suffering from skin disease, and one treatment to cure the skin disease was based on mercury, was using mercury products. So this is the reason why probably there was a sort of intoxication by using mercury products to cure the skin problems. So that's a typical kind of work which can be done by using the Fressen's technique. Let me move on to the second example. This is a work I was involved in. That was a collaboration with L'Oréal Research, the CNRS in France, and we had an active collaboration with the Louvre. So for that sort of work, we had access to large collections of little containers like those ones. These are reeds and little pots or little receptacles. And if you X-ray radiograph those objects, you find out that they are filled up with powder. So those, the powder inside is in a perfect conservation of state of conservation. It's in a perfect shape. So we were allowed to open up some of those little pots or containers, and we were able to sample some minute quantities of powder. So we did that in a large number of cases in order to understand how those cosmetics and makeups were prepared. And those objects were conserved in Egyptian tombs. So this is the reason why we had a large corpus of objects. We were able to look at many different containers of makeup. So to do that, makeup was very much used, extensively used across the whole society. It was used by men and women, by poor and rich people, by young and old people, whatever. So cosmetic was very important. It has social meanings, and it was also used in a number of rituals. So you see here a picture of the god who has 2 bags of makeup, of powder, and is offering those 2 bags to the god here. And there is a relationship between the practice around those makeups and the myth of Horus. This is the Eye of Horus. So if you look at representations of ancient Egypt on a number of paintings and frescoes and so on, you will see every time, we have the makeup around the eyes. So this is the experimental setup we were using here. So we were using a very high energy X-ray beam because these are lead-based products, very absorbing. So we needed to have high energy X-rays in order to penetrate through the powders. And we were using a very small beam to do a sort of grain by grain analysis in the powder. So the beam coming in here this way, and we have here the fluorescence detector coupled with a diffraction camera. So if I zoom up this particular part here, this is how diffraction works. You have the sample here, which is sitting here. So this is the powder, the Egyptian makeup. And the beam is deflected here in this way. And we can analyze this sort of pattern, what we call the diffraction pattern, in order to identify the phases present in the makeup, as well as we can look at the size distribution and look at several structural features inside the makeup. So this is particularly important to understand, well, to identify the ingredients and to understand the techniques of production of those makeup. So this is a zoom, a microscopic view of the powder itself. If we shoot the beam here, okay, we get this sort of diffraction pattern, and from this we are able to identify the phase. We say, okay, this is lead sulfide, which is galena. If now we shoot the beam at a different position, same sample, we have a completely different, different pattern. And we can identify here the material, the powder itself, it's phosgenite. So we can just identify the phases using this technique in a very efficient way. The thing which is interesting is to combine this technique with the fluorescence technique. So we measure simultaneously the diffraction patterns and the fluorescence emission. And what is interesting here, we see here those impurity patterns. We see here the fingerprints. So when we scan over this particular phase, we find that galena contains iron and zinc. These are the major impurities. But now, if we look at the fluorescence emission over this area for that particular phase, we find that the impurity content is completely different. So we have here clear evidence by looking at the impurity pattern, the impurity fingerprint, that those two materials have different origins, different provenance. And what we found out is that this material, it's a natural ore. It's very abundant in nature. So it's coming from the mines along the Red Sea coastline. But this material here was synthesized. And this is the reason why the impurity content was completely different. So we had here clear evidence that the productions or the origins of the materials were different. So we weren't able to identify natural lead ores, such as galena, and we were able to identify synthetic lead materials, in particular lead chlorides. So we went through that, and what we were able to show here, that was the first evidence of some chemical know-how, chemical knowledge 4,000 years ago. So we had a number of, a whole bunch of data, diffraction data, fluorescence data, using synchrotron radiation techniques, and we compared our results with existing literature. So we have ancient texts here, and those texts describe the ingredients, the recipes, the quality of the makeup, for which purposes, and basically we were comparing our results with those ancient texts. And doing this sort of work, we were able to really show the chemistry which was used at that time, and to show the know-how, the expertise of the people preparing those makeups. So it was a very elaborate mixture of natural compounds and synthetic compounds. So this is an example, a typical example of a recipe here. And so this is the source here. And it says, OK, we have to start with lithargium. Basically, if we want to translate that into modern terms, this is litharge, and this is lead oxide. And then we have to mix the lead oxide with rock salt. So this is sodium chloride. We make a solution of the whole thing. And then if we do that in warm water, we can produce this particular lead chloride. So we did that. What is interesting in that particular recipe here, you see, we have to be careful. We have to beat the solution a number of times. Then we have to strain out the old, and we have to mix new water. And that particular part is very important. So we did a number of simulations in the lab in order to understand this recipe and other recipes, and in order to compare our results with archaeological makeups. And if you don't replace the water in a sort of regular way, then because you have production of this of sodium hydroxide, your solution becomes very alkaline. You have a shift of what we call the pH. And then instead of, this is here the phase diagram, instead of producing this particular material here, this particular chloride, then you can precipitate something completely different. So 4,000 years ago, the Egyptians had enough knowledge and were careful enough, they were able to control the precipitation process. They wanted to have this material and not the one next to it. So by replacing the water on a regular basis, doing this very carefully every day for a long time, you need many days before you get enough quantity. By doing this very carefully, then you can produce this particular material. So the Egyptians were very careful by getting the right compound, the right chloride. Interestingly, if now you do the same sort of recipe, but you use natron, then you get another chloride. And this material, we also found it in the archaeological makeups, in the cosmetics. So this is another source of information we used. And it says here, those makeups can be used for eye care. So by doing this sort of work, we were able to demonstrate that those makeups were using as a sort of eye lotion. It was used for eye diseases, to cure eye diseases. So this is what it says here. Another remedy for curing the something disease of the eyes is to use the mesdemet. This is the word for the makeup. And it is translated here by Galina. So we know here, based on our work, that this was a sort of oversimplification. The makeup we found, they are made of galena, but we have also other materials. In particular, we have those synthetic chlorides. And these are the ones which make it possible to use those cosmetics, those makeups, as eye lotions. So by doing this sort of work, we have now a more precise translation of those recipes. We understand those recipes better. Okay, let me move on to the next example very briefly. This is work we did on a particular pigment, what we call it Maya blue. So before I go through this work, I just want to give you this short introduction here. We have a chance, by doing this sort of work, to look at materials which have been kept over very long time scales for centuries, for thousands of years, in very specific environments, sometimes in very hostile environments. So we have materials in buried, or materials in seawater, or in the desert, materials exposed to pollutants, humidity, different conditions of temperature, and so on and so forth. So by looking at ancient materials, we have a chance to understand the behavior and the transformation of materials under very long time scales in very specific conditions, things which we cannot do very easily in the lab. So this is one particular application of this sort of work. And what we did with the Maya blue, we did this sort of reverse engineering. Maya blue is a very, very stable pigment. So we said, OK, if we understand why this pigment resisted for so many years, for so many hundreds of years, then by trying to reverse engineer the material, we can make modern products, modern pigments, which are as resistant as those archaeological counterparts. So let me say a few words about Maya blue itself. These are here a number of examples where you see those frescoes and paintings and statues with this very nice blue color, well conserved. So this is a product, a pigment, which was used by the Maya people before the colonial times. And as I said before, the thing which drew our attention was the remarkable resistance of this pigment. It's very resistant to a chemical attack, and also it resists against temperatures. So we tried to understand that better. So this is here a typical fragment of a mural with the Maya blue, and we did a lot of analysis on those archaeological materials, and we did a lot of modeling in order to understand the resistance and the long-term stability of that particular pigment. So Maya blue is not a mineral per se. It's a hybrid material. So it's a combination between a clay. So this is a particular clay which we find in the Yucatan. So this clay is called paligorskite. And then we mix this paligorskite with indigo. So indigo is a natural organic dye. It's a blue material. It's just an organic plant. And basically, we mix them. We mix the two together. So those two are ground together and mixed together. Then we heat up the concoction. We heat up the mixture, and we get this final product. So sometimes we have to be very careful the way we prepare the material. Sometimes if we expose the material to a chemical attack, to an acid in particular, we see that the material changes color. So from blue, it turns into yellow. So that means that here, we didn't succeed to produce this nice pigment, because as you can see, it decomposes rapidly. So we have to be careful the way we prepare the pigment, and if we are careful enough, then we are able to obtain this blue pigment, and even if we expose this pigment to a chemical attack, to some nitric acid, we can still see that the pigment remains blue. So we did a lot of simulations in the lab. We did a lot of experiments using synchrotron radiation techniques in particular. And what we did at the end, we were trying to mimic the Maya blue. So once we understood what the Maya blue was all about, this mixture between a mineral, a clay, and an organic dye, we were trying to do the same with modern materials. So we tried different substrates, different minerals. We tried different clays. We tried different zeolites. And then we mixed those materials with indigo, and we were trying to mimic, to reproduce the high stability of the pigment. So we did that in a number of cases, and we were able to design a similar kind of analog pigment, very stable, which can resist irradiation and which can resist a chemical attack. So this is here a view of that particular pigment. This is the modern counterpart, the modern analog of Maya blue. We can see here the indigo molecules which enter inside the material, which diffuse inside the cavities and the channels of the substrate. So we see here the coloration here. We see the indigo molecules diffusing inside the substrate. And this is here a view of the in situ experiment we were doing using synchrotron radiation in order to understand the process of formation of the hybrid material and the process of diffusion of the indigo molecules inside the mineral substrate. Okay, the next example is about heritage management, or let's say we have a number of issues about degradation of materials, degradation of objects. And this is true for a wide range of materials, of objects. It's true for metal, wood, glass. We have a number of monuments, a number of paintings which suffer degradation. So the key question is, how can we stop this degradation? So we need to understand the degradation process, and we need to find proper preventive, proactive strategies to prevent, to stop those aging or degradation processes. So this has a huge impact for obvious reasons. And we want, of course, to pass this heritage to future generations. And one idea is that it is important to use the power and the capabilities of advanced techniques, such as synchrotron radiation, in order to contribute into this sort of topic. So let me give you a couple of examples. This is a drawing, a prehistoric drawing on a wall of a cave. So you see here the nice let's say brush strokes, or the drawings here of animals. And the concern here is that those drawings are kind of fading with time. So this is here a view, and you have here the growth of this white layer which goes over the drawings. So progressively the drawings disappear because they are recovered by this white layer. So this particular team here did a lot of work in order to understand this process. So this is here the substrate, the wall itself. Okay, so it's made of calcite, and then on the top of the wall here, you have the pigment. This is a black pigment, manganese oxide, and as you can see here, on the top of this layer, so this is the pictorial layer. On the top of that, on the top of the chromatic layer, you have the growth of this additional calcium carbonate layer. So this is the reason why after some time we don't see the drawing anymore, because it's covered by this growing layer of carbonate. So that depends on the conditions inside the cave, on the pH, on the humidity, on the temperature, on the presence of microorganisms, and so on. So there is a complex dynamic in order to account for the growth of this particular layer. So this is work done at a synchrotron radiation facility using a very small beam, and we are able to do this sort of mapping in order to identify the different phases and the way those different layers are superimposed on each other. Another example is a superb piece of work which was done on this particular warship here. This is a warship which sank in the harbor of Stockholm more than 300 years ago. And it was recovered back in 1961. It was taken out of the water, out of the seawater, and it was exposed in a museum. And what happened here in that particular case is that rapidly there were signs of deterioration. There were growth of salts and appearance of acidity over the boat. So the warship was rapidly deteriorating in the museum. So there was a lot of concern about this. So this particular team here, Sandstrom and collaborators, they did a lot of work, in particular, using the radiation synchrotron facility at Stanford in order to understand the process, what is going on. Why is this wood, the wooden boat, why is it degrading so rapidly? I don't have time. I'm not. Yeah, time is running fast, so I'm not going to go into the details of this result, of this story. I want just to show another example here. This is a work done by Jennifer Mass, who is a material scientist in the conservation laboratory of the Winterthur Museum in Delaware. And she did a lot of work using different synchrotron radiation facilities at Stanford, Grenoble, Cornell. And she was interested by the deterioration process on paintings by Matisse. So she took small fragments, small cross-sections out of the original painting. This is how it looks like. This is the scale here, 550 micrometers. So it's a very tiny fragment. And again, using synchrotron radiation beams, very small beams, she's able to do this sort of mapping. And she's looking here at the distribution of sulfur, silicon, and lead across the different chromatic layers of the painting. And the question mark here is, what is the degradation process? Basically, what's happening here is that the yellow here, this yellow is progressively losing its color. So this is more work done at synchrotron radiation facilities on the same paintings. And basically, the yellow, which was used by Matisse to paint this masterpiece, the pigment was cadmium sulfur, or cadmium sulfide. And you see, after a while, cadmium sulfide is not the predominant phase anymore. So there are still, let's say, traces or still some cadmium sulfide, but progressively the cadmium sulfide, the original pigment, is being replaced by other pigments, in particular cadmium carbonate and cadmium sulfate. So because we have production of those new phases, then we have disparation, the cadmium sulfide disappears, and we lose the yellow color. So there is a very extensive work being done on that in order to understand the process, how the original pigment degrades into those products. So what is interesting here, once you've done this work, you can understand, you can propose some strategies or some measures in order to stop this degradation process. And I like this part very much because the art historians, when they looked at this particular painting, they say, oh, there is some sort of chromatic frigidity. And the master, Matisse, in that particular case, the master was using a very cold palette. So the yellow is not very nice. So the visual aspect of the painting is very different. And there is a whole description by the art historians in order to understand, okay, why did the master use that particular color? Why is it so, it's not very nice? Why is it this way? And one conclusion was, okay, the master was using cold chromes, chrome pigments, instead of cadmium yellows. So there was a misinterpretation here. The understanding was that cadmium yellow was not used anymore. The master was using different kinds of pigments, different yellow pigments. And it turns out that this conclusion was wrong. I mean, if we do the analysis, we use synchrotron radiation beam, we do the mapping, we look at the elemental composition, it's still cadmium yellow, but it turns out that the cadmium yellow is transforming with time. There's a degradation process. So it's not so much that Matisse was using a different technique or different pigments. It's just that the initial pigments he was using, those pigments degraded with time. So what we see now doesn't reflect how the painting was a few years back. Okay, so let me now go through my last example here. This is a very nice piece of work which was done by those people, in particular Joris Dick and Koen Janssens, and they were interested by this painting done by Vincent van Gogh by the end of the 19th century. So this is a painting kept in Paris, and it's called Patch of Grass. So this is how it looks like. And there was suspicion, if you X-ray radiograph this picture, there was suspicion that maybe there is something underneath this particular landscape. So they brought this painting at Hasilab, which is another synchrotron radiation facility, and they scanned the painting in order to understand the different pigments, the different layers of pigments. So the beam here was raster scan, and these are the results. So this is the area, that's about 15 to 17 centimeters squared. So this is the area which was scanned. It took about 2 days to do this experiment. So this is a fluorescence mapping. We're looking at the emission from zinc. So this is a zinc-based pigment, and you see that in order to produce this grass, to produce this landscape, Van Gogh was using a zinc-based material. If we now look at the signal emitted by barium, we have the signal from barium. So zinc-based pigments were mixed up with barium-based pigments. Okay, so these are the pigments which are on the top surface here. Now, if you continue the analysis and you look at the other characteristic fluorescence emission lines, you find here emission from lead. So this is another pigment. This is what we call lead white. This is the preparation layer, which is underneath the chromatic layers. So we have here the green, brown, white layers. Underneath, we have a white layer. This is the preparation layer. And if you continue the analysis, you look at other signals, other emissions, you find here some emission from antimony and mercury, and here's the picture which you can get. So obviously, using those particular pigments, that canvas, that particular painting was used to make this portrait, and what happened, Van Gogh reused that particular painting. He recovered, he superimposed the landscape on the top of that portrait. So the pigments which are used for that particular work here, for the portrait, these are Naples yellow and vermilion. And it is interesting to compare. This is what the conventional X-ray radiography gives compared to this sort of work. Okay, so here this is a fluorescence mapping. You see the individual components, the individual layers, and you have a much better contrast using this technique as opposed to X-ray radiography. This is work which was done, this is a painting by Rembrandt. this particular painting here was analyzed at different places, but it came to the NSLS, it came here on site, and Peter Siddons was involved in that work back in 2009, and there was an issue about the authenticity of this portrait. Was it done by Rembrandt himself, or was it a copy? So there were different measurements, and in particular there was X-ray fluorescence measurements, and part of the work was done here. And there was a definitive conclusion that this portrait was done by Rembrandt himself. So if you look at the fluorescence emission from lead, this is what you get here. So you have a picture which is very similar to that one, okay? So most of the face here is composed with a lead-based pigment. But now if you look at another emission, you look at the copper emission, the copper signal, using this fluorescence technique, you see a completely different motif. So you see here this face with a sort of a hat, sort of beret or turban or whatever, and you see here the dress. There is a sort of a color here which is different from what it is here. So clearly, underneath this portrait, there is another attempt, another drawing. What is interesting here is that this particular drawing here is very similar to that self-portrait which is kept at the Metropolitan Museum. So this is an existing painting, and there are a lot of similarities between this painting and that one. So this one now is recovered by this portrait, but by looking at those analogies here, there is the current thinking is that very likely this work was done by Rembrandt himself. All right, so this is here the experimental setup which was used at the NSLS. So this is the painting itself, which was mounted on a very large kind of scanner. And this is how it goes. So this thing was designed by Peter Siddons himself. It works at the NSLS. And this is, so we see how we can scan the entire painting to do this sort of analysis. So you can recognize here the portrait here. All right. So let me come to a conclusion. In a number of cases, we found that using synchrotron radiation can be very useful. It is something which is complementary to the laboratory techniques. We have to combine laboratory investigations and synchrotron radiation techniques. So in a number of cases, we use synchrotron radiation where we want to look at different scale length. Synchrotron radiation techniques are very useful when we want to have structural information as well as chemical information, and we want to look at major elements as well as trace elements. And the power of synchrotron radiation techniques is when we want to do imaging. So a lot of work now does 2D or 3D imaging on artifacts and archaeological objects. So very soon we're going to have the next generation light source. So this is NSLS2, which is under construction, and it should start operation in 2015. And no doubt the sort of work I just presented could be done, we will be able to do this sort of work at NSLS2 as well, using the high intensity and the very small beam size. So let me just conclude here by saying that in the United States over the past years, there has been an increasing interest in that particular field. We have more and more meetings and workshops and conferences about this particular subject. There was one at the users meeting back in 2009. Next year, we're going to have a golden conference on that particular subject. But let me draw your attention on that one. We are going to organize, Brookhaven National Lab is going to be a partner of this conference. We are going to organize this particular conference at the Metropolitan Museum in June next year. So we will have a chance here to see all the experts, synchrotron radiation scientists, as well as curators, conservators, archaeologists, art historians, and the idea is to get those people together, talk to each other in order to work together. So last but not least, I want to thank the people I've been working with. In particular, I had a very strong collaboration with Philip Walter and his team. So Philip Walter is the head of the Laboratory of Research, which is located in the basement of the Louvre Museum. And it's run by the Ministry of Culture and the CNRS. And I had a very active collaboration with Philip Walter and his team. These are my colleagues at the Nail Institute. These are my PhD students who helped me to do this sort of investigations on the Maya blue and on the Egyptian cosmetics. I used the ESRF a lot, so these are the people I worked with. And finally, I would like to thank you for your attention. Thank you very much.
We have time for some questions. Down here.
Technical capabilities that you talk about are clearly very dazzling, but how much of an issue is it getting people who are traditionally trained in conservation techniques to realize the value of the new things that you're able to do? Do they instantly embrace this, or is this troublesome?
Yeah, there is a sort of a cultural gap, I would say. So this is the reason why we have to go through those different conferences and workshops. We also are trying to organize training sessions in order to have young people, young material scientists, for example, trained in those techniques. It is true that it takes time. It's a matter of trust between people working at museums and ourselves. We have to build up relationships. We have to build up strong collaborations. So usually we start with ordinary objects or with mock-ups, and then progressively we build up a program. You can't do that like this. I mean, it takes time because there are issues about, oh, I mean, this is too complicated. I don't want to bring my object to the synchrotron radiation facility. I mean, the access to beam time is an issue. Security is an issue. Storage is an issue. Beam damage is an issue. So there is a lot of preparation work before we're able to do this sort of work. But for example, I mean, what I showed about those hidden paintings, for example, I mean, the power of using first sense techniques is so huge. I mean, there was no way this could have been found. I mean, it was difficult. Yeah, that's right. That's right. So, but you're right. I mean, it takes some effort and some. It's a matter of confidence and trust between the people.
Steve?
You mentioned it briefly just a moment ago. Do you have to worry about radiation damage from these very intense sources and beam damage?
It could be an issue, yeah. Particularly when we have organic materials. If we have resins or oils, they degrade very rapidly under the beam. So what we try to do is we try to scan the painting, for example. We try to scan fast enough. So we have high photon density, so we can quickly scan across a surface. So as a result, we minimize the exposure time, and we minimize the radiation damage. But we have to be careful with that. Yes, that's right. It might be an issue. As long as we have minerals, inorganic materials, inorganic pigments, it's fine. It's very stable. If we have organic materials, it's a different story.
And the last thing that you showed with the imaging, you didn't have to worry about damaging the painting at all.
No. Well, no, we didn't see any effect. That's fine.
Okay, there are refreshments in the lobby. Let's thank our speaker one more time.